Okay. Now can you see the writing up?
Yes, sir, we
Yes,
can
sir.
see it.
So when we talk about buckling, we usually mean something like this, that you have a very slender structure. Okay, so very slender structure. So imagine that this thin line, well, you don't have to imagine, I'll just draw it properly. So it's like a beam, but a vertical beam. So there are some kinds of end conditions here, and we are going to go into that in proper detail later on. But we usually understand that suppose this is very much like those two force members which you are very familiar with from your first year basic engineering mechanics. Now, when we talk about buckling, what we usually understand it immediately is that if this force becomes too large, then what can happen is that even though this is an axial force, there may occur some kind of a bending. Okay, so this vertical beam that deflects and becomes like this. It is almost like magic. Now, this kind of behavior is, of course, referred to as buckling, but buckling itself falls under the very broad category of uh, mechanical phenomena, which is referred to as instability. I'm sure you have heard of this word instability, but as you go into higher and higher classes, you will come across more and more examples of such kind of unstable behavior. So just like we do at the beginning of almost every chapter, I want you to give me certain examples from your day-to-day life where you see these kinds of buckling, and I would be very happy if you can give me some examples of instability which directly do not connect with this kind of a picture where you have a beam-like thing or a very slender structure, but something completely else which may not have anything to do with a solid mechanical structure. So I want you to think very broadly in terms of buckling and even more broadly in terms of instability, and try to give me some practical examples. And then we'll go into the various equations and the mathematical modeling and all those things. Okay, so let's have a discussion for a few minutes regarding such practical examples. Tell me, what do you think would be some practical examples of buckling and instability?
You just
So like the railway tracks, like
failure
in
of bridge.
summer when they expand, like they can like buckle. Like that should be an example of buckling, I guess.
Right, because we already discussed that in the context of a similar discussion at the beginning of previous week's discussions. Yes, that is true. Any other example? Try to free up your mind and think very, very broadly. So I'm talking about buckling as well as generally instability. Any kind of unstable behavior that you think. Okay, it may be from fluid mechanics, it may be from electronics, whatever. Whatever comes to your mind, feel free to state it. It can even be from
KS
nature.
instability.
Yeah,
KS instability.
I cannot hear you. Please say that again.
So Kelvin Helmholtz instability.
Kelvin Helmholtz instability. Did you say that?
Yes, sir.
What do you mean by Kelvin Helmholtz instability?
So like I heard a lot, like it's something related to that flow separation or something, like some vortex shedding.
Okay, okay. See, you can say names, okay. You can say, I mean, rabbit tiger instability and tomato cauliflower instability, but it's better to actually identify what the phenomenon is rather than just knowing the name. Okay, so what I want you to describe is the actual thing which you observe. So I will give you a hint, okay? So maybe many of you are not familiar with this term, although I think in your +2 some of this was discussed as part of physics. So just to refresh your memory, uh, in general, an unstable behavior would be termed something like this, that you have some kind of a structure or some kind of a configuration of anything, and then if you disturb it slightly, whether that object or that configuration or that structure has a tendency to get restored to its original configuration or not. If under the influence of the slight disturbance, it gets disturbed and then does not return to its original configuration, but keeps on like becoming more and more disordered, and it keeps on changing its configuration further and further as a result of just that small disturbance, then that is an unstable kind of system. Okay, this is the very general thing without any equation or any sophisticated statements. This is the general understanding. Okay, this is the, I mean, an unstable system. Okay, and it can carry over to like people's personality also. So some people are very calm and composed. Under the influence of various kinds of disturbances, they maintain their cool. So they are referred to as very stable kind of personalities. Okay, so as opposed to some people who under the influence a little bit of a disturbance or a perturbation, they will just, I mean, fly off. Their temper will fly off, and those are very unstable personalities. Okay. So it can refer to many things. So now tell me.
For a palace of plastic cups or glass something. So like we arrange glass in like in a palace kind of shape, right?
What? Your audio is not at all clear.
Like sir, if we can think of like if there's like a hill, suppose, and there's like a round rock on top of it, like at the summit, basically. So if it gets pushed, it will just roll down. It will never go back. Something like that.
Somehow I cannot hear anything. Maybe something's wrong with my audio. Can someone maybe write down in the meeting chat what one of you is saying? Oh, cups and glasses. Right. Yes, good example. If we consider, so Shomit is saying if we consider a round boulder on top of a hill. Yes, that's a classic example that is given in physics to discuss unstable behavior. Yeah.
Sir, a pendulum without damping.
A pendulum without damping. So a pendulum without damping. So what's so special about the damping? Suppose there is no damping, and suppose there is damping. What's the difference?
Sir, if there is damping, then it would come to its state of rest. I mean, it comes to its initial position. But if there is no damping, then it continuously oscillates when a small disturbance is injected.
You mean damping in the form of air resistance also?
Yes, sir.
Very ideal conditions. Okay, but in a
Yes,
real
sir.
in a real pendulum, it always comes back to its original position, right? So
Yes,
a
sir.
normal, simple kind of, I mean, clock pendulum, we can refer to it as a stable system. Okay. Somali Jana, can we consider aerodynamic flutter as a case of instability? Certain parametric regimes of it, yes. Okay, but that's not a day-to-day life example. Very sophisticated example. I like the example of this cups and glass and this pendulum. These are things which are commonly found around us. I'm sure you have, you all have, taught, taught a little bit about uh, turbulence. So what about that? Do you think that is an example of instability? I mean, you have not been taught the chapter of turbulence maybe, but as part of your initial introduction to Reynolds number and pipe flow, maybe some things were mentioned. Do you think that would be an example of instability?
Yes, sir, we can consider that as instability in the flow. I
Right.
think yes.
Yeah, but we have to be a little bit careful there because it depends on the kind of Reynolds number you are working with. Okay, because beyond a certain Reynolds number, you will or below a certain Reynolds number, it will not be possible to transition into turbulence, or uh, beyond a certain Reynolds number, you cannot have any kind of stable behavior. So subtle things are there. Okay, so the point that I wanted to highlight through these discussions is that whether you take the example of this cup or glass or pendulum or uh, this fluid mechanical examples, uh, the hallmark or the distinguishing feature in all of these things is that uh, if you disturb them, they may have a tendency to come back to their original configuration. For example, if you have a laminar flow, it may come back to the laminar flow if you disturb it, or it may not. Okay, so whether it comes back or it does not come back will enable us to distinguish it as stable behavior or unstable behavior. Okay, so this is the general idea. So there are some other examples also which usually people do not identify uh, as also examples of unstable behavior, but they are. Now, in nature, you will find certain kinds of very beautiful structures. For example, the edges of a flower petal, okay, or the edges of a leaf. Uh, you will also find uh, examples in the beautiful forms of uh, shell structures which are present in sea animals. Okay, like sea animals have a protective shell over their body, and those shells have very complicated structures. Okay, so uh, those are very hard structures, of course, but whether it's a flower petal or a leaf, leaf means a plant leaf, okay? So you can see some kind of, let me go to the writing here. So the edges of a leaf are sometimes like this. The edges of a flower petal, they are sometimes like this. And the shells of many sea animals, they are also like this, or they can have certain spikes also like this. So all these different kinds of structures that you see, they are also as a result of the the inherent instability that is present uh, during the growth of these kinds of bodies, okay, of these various kinds of organisms. Like flower, when it is growing, some kind of unstable behavior occurs during its growth. Uh, the growth of a leaf also some kind of unstable behavior, which is why these kinds of wrinkled like shapes they appear. Okay, and fundamentally, this is also an example of buckling. Okay, it is not a buckling like a beam buckling, but this also is an example of buckling. This also is an example of buckling. Okay, so I mean, both nature as well as man-made objects are filled with beautiful examples of unstable behavior. It is not always that unstable behavior is bad. They are actually sometimes like inherently the part of life and growth, and as Mother Nature works. In our human body also, one of the most important organisms of the human body, the brain. Okay, so you may have seen pictures of the brain. So there are I mean, numerous folds in the brain. So our brain, it has like these kinds of folds, fold kind of structure. If you take a slice of a brain, like an anatomical slice, then you will see that our brain has these kinds of deep ridges. Okay, and they are absolutely intrinsic to the growth and the well-being of the like the healthy structure of the brain. And when the baby is growing, this kind of ridges they form at the very nascent stage, And these are also examples of unstable behavior and very much deeply connected to solid mechanics. And believe it or not, there are actual hardcore solid mechanics studies, very hardcore solid mechanical studies, which are dealing with the mathematical modeling of the developmental biology of these kinds of things. Okay, so this area, the study of buckling is, I mean, is not at all limited to just these traditional kinds of engineering structures. Rather, it covers a very wide variety of things. Okay, so with this introduction, it is time to cover the syllabus properly. Okay, so our intention would be to obtain some kind of equation and formula associated with this kind of behavior, and we will go into that. But usually what is done is, as a very brief introduction, we do not consider this structure, rather we consider some sort of an easier structure which is borrowed from rigid body mechanics. Okay, this is not rigid body, this is a deformable body. You know all that by now. We are not going to take that example first of all, we are going to take that example second, but first we are going to take an easier example from rigid body. So our example is like this. It is almost in every undergraduate textbook you will find this kind of an example, that you have a beam like this. Okay, not a beam, I should not say a beam, you have a rigid bar like this. All right, and it is let's say it is connected via a pin joint to this kind of a vertical guide. So that this end, it can move only up and down, and it is free to rotate about this hinge joint. And here there is another rod present, another bar present. Like this. And at this end also, there is this another pin joint or hinge joint. Both of these bars, they are rigid, okay? And at this point, it is not just freely pinned, okay? There is something special there. There is a torsional spring there. Okay, torsional spring. Maybe I just extend a little bit. Something like this. Okay. Maybe I should draw it the other way around. Yeah, this is better. All right. Now what is done is we press down on it like this with a force P. And then we consider the free body diagram of this thing. So even before that, you try to think of it like this, that if we just press down on it, nothing is going to happen because this is rigid, this is rigid. There is not going to be any movement. But suppose for some reason you slightly disturb it. Okay, you maybe just slightly poke this thing on this end. Okay, just poke it a little bit. So if you poke it a little bit, what will happen is that it will slightly get deflected. So under the deformed configuration, it will look like this. So it will look like this. Remember that this is a rigid, okay? So this is not going to get curved or anything. This is going to remain straight. This is going to remain straight. Now, because of this angle of deflection, this torsional spring, it is going to exert some kind of restoring torque at this end in order to bring it back to this vertical position. Okay, so okay, you understand what is happening here. We poke it a little bit. This downward force is acting. If this torsional spring was not there, it would completely come down. Okay, but this torsional spring is resisting the change in this angle, this increasing angle of deflection between the two rods. It is resisting that change, and it is trying to bring this configuration from this bent one to this straight one back again. So if we want to draw the free body diagram, let's say of this upper bar, you tell me the kind of forces that it is experiencing. On the top,
Here the torsional spring is along the beam, no? The torsional spring axis.
torsional spring axis. What do you mean by axis? Axis is into
Means
the
that
plane of
the
the
plane
screen.
in which it is lying is perpendicular, no? To
Yes,
the
yes,
beam.
it is into the plane of the screen.
Okay.
Yeah. So at this end, there will be an opposite force P, and there is going to be a restoring torque also. Okay, you tell me one thing. Suppose this angle is theta. What is this angle? Then this is theta. These two are of the same length. Okay, so this is an isosceles triangle. So this is theta, means this is also going to be theta. This angle is going to be 180 degree minus theta. So this is also, this is going 180 degree minus twice theta. So this is going to be twice theta. So if there is a deflection of twice theta, this torsional spring is going to exert a restoring torque of K, where K is the torsional stiffness, K times twice theta. Okay, just like in a linear spring, you have K times the deflection. So also in a torsional spring, it is K times the angle of deviation or the angle of deflection. Angle of deflection here is twice theta. So it is K times twice theta. So this thing will have a magnitude of K times twice theta. Okay, so now what we want to do, we want to do a moment balance of from this free body diagram. Okay, so if you do a moment balance, tell me what it will be. Take this length to be L. Okay, take this length to be L. So this is L.
So PL sine theta.
PL, so this angle is theta. You're right. This is PL sine theta.
Minus K times 2 theta.
Minus K times twice theta. That is going to be equal to 0.
0.
Okay, this is the moment balance equation. Okay, so where you are basically taking the moment balance, I mean, you can take it either about this end or this end, story is the same. Okay, so the equation that we are having is this PL sine theta is equal to K twice theta. Okay, so actually in your textbook, I think this this length is given as L by 2. And that makes sense because later on for the entire beam, we are taking the length to be L. So in this analogous example, we'll take this length to be L by 2, this to be L by 2. Okay, so just to match with your Beer and Johnson. So we'll take this as L by 2, L by 2. Now, what we are going to say is that if this theta is small, okay, for small theta, sine theta is almost equal to theta, which means that the equation that we are having is PL by 2 theta is equal to K twice theta. And from here, what we are going to obtain is that P is equal to 4K by L. Now, this thing that we have obtained seems like no big deal. Okay, from a simple moment balance, we have managed to do this. But from this simple equation, we can obtain some very important lessons. First of all, you think that this is the equilibrium condition like this. But in this equilibrium condition, as long as this theta is small, the theta itself does not appear in this equilibrium condition. Okay, so this is independent of that theta as long as theta is small. This is an important thing to note. Next, you understand that suppose this P was less than this value. Okay, suppose P is less than 4K by L. What is going to happen then if P is less than 4K by L?
Sir, I think it will move back to its original position.
Exactly. So you try to think of it almost like a pendulum concept. Okay, so if P is less than 4K by L, okay, so structure becomes so completely stable. Okay, stable means, remember that this kind of a configuration is coming out only because you had poked it a little bit. Okay, you had disturbed it slightly, and that disturbance, when we are saying that we are disturbing it slightly, that is basically translating to the concept that our deflection here is this small theta. Okay, so poking it slightly means theta is small. So as long as theta is small and the value of this P is less than 4K by L, it is guaranteed that this structure is going to be stable, meaning that under the restoring action of this torsional spring, it will move back to its original vertical configuration. Okay, this is a very simple, straightforward concept, but extremely important to understand. Next, if P is less than greater than 4K by L, then it is going to be unstable. Unstable means that we poke it slightly. That means we, as an agent of disturbance, we introduce a small angle of deviation theta, but the inherent nature of this structure is such that even under that small disturbance, it completely flies away from its original vertical configuration, meaning that as when this P is greater than 4K by L, just by the small introduction of this theta, what is going to happen is that this restoring force is not going to be able to sustain the influence of this P. And just after we have introduced this small theta disturbance, this theta is going to keep on increasing. So it is going to become more and more deflected, and this entire structure is going to collapse. Okay, of course, such a drastic thing doesn't happen. Before that, some other things happen, but you understand that under this condition, basically the structure is going to be unstable. Unstable to the small deflections that we introduce externally. What happens under this condition? Okay, this P is equal to 4K by L. What kind of a thing is this? So this is referred to as the condition of neutral equilibrium. Okay, neutral equilibrium means that as long as this theta is small, so maybe theta is something like 2 degrees or 3 degrees. So it doesn't really matter whether theta is 1 degree or 1.5 degrees or 2.2 degrees. As long as theta is sufficiently small, with P is equal to 4K by L, this thing is always going to be stable, meaning that when you poke it and make it disturbed like this, it is going to remain in that disturbed configuration in a nice stable kind of manner. Okay, it is neither going to fly off on that side, nor is it going to be restored back to its original configuration. Okay, it is just going to remain like that in that bent configuration, because there is a nice balance between the restoring force of the spring and the force P. Okay, very, very straightforward, simple concepts. It's almost as if I'm discussing +2 physics, but in the context of what we are going to discuss later on, and in the context of the overall topic of unstable behavior, this is very, very important to understand. Okay, with this background knowledge, let us actually go to this thing. And here we are going to take help of the same kind of things that we did in the deflection of beams in the earlier chapter, but just a little bit of a twist is there. So let's see. So we again considered this thing, this vertical beam. And please note that when we say vertical beam, there is actually a terminology for this. A vertical beam is usually referred to as a column. Okay, so vertical beam, you don't have to keep on saying vertical beam, vertical beam. In actual engineering practice, a vertical beam is actually referred to as a column. All right, so its two ends are going to be pinned. Okay, this is one pinned end. This end is also pinned, and maybe it again has this kind of a guided support. So this guided support is just to ensure that this end, it moves down just up and down like this. And of course, there is this force P on this. And just like before, we want to draw a free body diagram in order to understand what is going on here. But even before we draw a free body diagram, just try to understand it in exactly the same fashion that we understood the previous problem involving the rigid body, those rigid body links or the rigid body bars. Here also, you try to poke it a little bit. Okay, so if you poke it a little bit, just a little bit of a disturbance, what is going to happen here? It is going to again become bent. Okay, we just poke it and leave it. So if we do that, then this thing is going to become slightly bent like this. Question is whether this bent configuration or this situation, this is going to be stable or not. That is what we want to investigate. So in this bent configuration, we want to draw the free body diagram. Okay, so just like before, we are going to draw the free body diagram, but you see in the previous problem, we took just the upper part. Okay, here also what we are going to do is, in keeping with our previous studies, we will take a cut section of the beam. We will take a cut section somewhere here, like this. So this this beam will look like this here. Furthermore, we are going to take our x-axis downward like this and our y-axis like this. So you can almost see that if you just rotate your page or you rotate the screen by 90 degrees in the anti-clockwise sense, okay, the whole thing, this will look like this. Okay, this is going to look like this. This is x and this is y. So exactly the same kind of coordinate axis orientation which we had considered previously. Okay, that's the motivation of taking our x and y like this. All right. Now, the deflection at this part, this is y. This much is y. You understand that? This is y. Okay, and you have a force P acting like this. And you also have a force P which is acting from the rest of the cut part on this part. Anything else that is acting here?
Sir, a torque.
Don't say torque, moment.
Yeah, just a moment.
Please note that I have drawn it in this anti-clockwise sense because I want you to go back to this picture, take a cut section here, and consider the kind of free body we used to draw. Okay, so just to clarify, okay, so we have this force P, we have this force P, so this P is this P, this P is this P, and then we used to draw something like this. Okay, this bending moment. This is the positive sense of the bending moment which you used to draw. Same thing that I have drawn here. Okay, just in a vertical configuration. Now you tell me the expression of the moment from here. Tell me.
So P
M
times
is
of y.
Py.
Tell me.
M is equals to minus Py.
M is equal to minus Py. Very good. So basically M plus Py is equal to 0. So M is equal to minus Py. Very good. Okay, the moment you have this, then in terms of what we discussed in the previous chapter on the deflection of beams, can we not again start with the same kind of equation? Meaning that we want to start with this EI d square y dx square is equal to M. This was our starting point. Okay, so this is the second order differential equation version of the deflection of beams. And here we are going to, so this is equal to minus Py. So I transpose it to the left hand side. Then I divide throughout by EI. Just to make this equation a little bit more clean looking. So P by EI times Y. Please note that unlike the previous chapter on the deflection of beams, where we were considering the horizontal orientation and everything, there the expression of the moment, it involved not Y but X. Here it is Y. Okay, because there the deflection was taking place as a result of transverse load on the beam. So it was a case of direct bending. Here also bending is occurring, but this bending is as a result of the unstable or potentially unstable nature of the column. Okay, the driving force of the deflection is actually this force P, which is axial in nature. It is along the axial direction of the beam. So the moment, it is actually involving the Y component, the Y variable, not the X variable. That is an important difference from the previous chapter. Now you see this P is a positive quantity. Young's modulus is definitely positive, and the second moment of area or the moment of inertia I is also positive. So this numerator is positive, denominator is positive. Overall P by EI is a positive quantity. And because it is a positive quantity, I want to replace this combination by a single variable, but in order to ensure that it is actually a positive thing, I will say that P by EI is equal to K square, okay, which ensures that this is a positive thing. Okay, plus there is another motivation of writing this thing as K square, you will soon see. Okay, so what I want to do now is solve this equation. D square y dx square plus K square y is equal to 0. You tell me, how do I go about solving this equation?
Sir, solution will be y naught sine k.
Suddenly you are telling me solution. Tell me how I solve it. Maybe for this simple kind of equation, it is obvious to you, but tell me how.
So let's assume y solution y equals to e to the power 80. Oh, sorry, ey.
How it is not here. Yeah, so assume y is equal to
E to the power lambda x.
e to the power mx. Okay, so this is, I believe you have done these things in your first year maths, right?
Yes, sir.
Okay. So if we now substitute this thing here, what happens? This is a second order derivative. So from here we'll get m square. From here, so m square y, okay, because you are going to get m square e to the power mx. So let me write that. This is k square. This is again e to the power mx equal to 0. So from here, what we are going to obtain is this m square plus k square is equal to 0. From here, what we are going to obtain, m is equal to, tell me,
Plus or minus I.
plus minus ki, where I is the imaginary unit. That means my solution will be what? Of what form? So y is equal to c1 e to the power m1x plus c2 e to the power m2x, where m1 is equal to plus ki, m2 is equal to minus ki. Okay, expand it by De Moivre's theorem. What is it? Tell me.
So cos kx plus eta sin kx.
And this one?
Cos kx minus sin eta sin kx.
All right. So I want to collect the cos kx terms together. C1 plus C2 cos kx plus IC1 minus IC2 sine kx. So this one I will call A, this one I will call B. Okay, so my solution for y, it will look like this: A sine kx plus B cos kx. Okay. Now I have, so my original equation was a second order linear differential equation. We have not done two integrations, but effectively what we have done is two integrations because we have found out the solution of this equation. There is no integration steps involved, but it is fundamentally equivalent to doing that two step-by-step integrations. Ultimately, for the solution, we have found out, as expected, an expression involving two unknown constants, A and B. Our job is now to find out the values of this A and B if it is possible. Okay, let's try that. So our y is now A sine kx plus B cos x. What are the conditions we must impose? Go back to the diagram and look. At this end there is a free end and this one is a this is a pinned end and this is a pinned end. So tell me, at x equal to 0 and x equal to L, what conditions I must apply?
So y is 0 at x equals 0 and L.
Yes. So please do not be confused that this point is moving downward. That downward movement has nothing to do with disturbing y. At this point, y is guaranteed to be 0. Okay, because y is in this transverse direction. Okay, because of this vertical guided support, this y is guaranteed to be 0 at x equal to 0. Okay, so if you substitute x equal to 0 here, what remains? This b. So b is equal to 0. Next, at x equal to L, what do you obtain? With y equal to 0, A sine KL is equal to 0. Now you tell me, what do I do?
So KL is integral multiples of pi.
Tell me properly. So suddenly you are saying sine KL is multiples of pi. Why? Why not A equal to 0?
Sir, if A and B are 0, then we'll get y is 0 for all x. But
Yes.
practically, when we are seeing, it's not possible.
Right. So this is an important thing to say. Let us not bypass it. Okay. So if we say that if A is equal to 0, then already B is equal to 0, then our y is equal to 0. And this is a trivial solution. Trivial solution does not mean it's a bad solution or anything. Okay. It's meaning that from this kind of a thing, this kind of a bent shape that we are considering, if y is equal to 0, then this kind of a bent shape is never ever realized. And then there is no possibility of investigating the buckling is happening or not. Okay, we do want to consider under what conditions this buckling is happening, whether that is stable or unstable or whatever is happening associated with that. So if we fall back to the condition of A equal to 0, there is nothing wrong with it, because you will definitely see that if P is small enough, then this vertical configuration is a nice stable configuration. Nothing is going to disturb it. Just magically it is not going to bend like this. It is only for sufficiently large values of this P that this kind of bend shape is at all going to be realized. Okay, so y is equal to 0 refers to those kinds of very stable configurations with P very, very small. Okay, so this is a trivial solution. It's an important solution, that vertical configuration. That's the usual thing that is going to happen. But we actually want to investigate what happens for large values of P when the bending, when such kind of buckling induced bending is actually occurring. So for non-trivial solutions, okay, for non-trivial solutions, meaning that the bend shape is actually there, we must have that sine KL is equal to 0 with A not equal to 0. Now sin KL is equal to 0 can be realized for various combinations. So KL is equal to n pi in general will give us this this condition that sin KL is equal to 0, where n is equal to, of course, 0, 1, 2, 3. 0 is again a trivial solution, but 0, 1, 2, 3, all these things. Okay, so our so if we go back to this thing, okay, this one, P by EI is equal to K square. Okay, what do we obtain? So you see this K is coming out to be n pi by L, right? When K is equal to n pi by L, guys, just give me a second. Okay? Okay, so as I was saying, when K is equal to n pi by L, we have K square is equal to n square pi square by L square. Now K square we have already the expression for this is P by EI. So this is n square pi square by L square. So P is going to be equal to n square pi square EI by L square. And the first, so you see this P is equal to n square pi square EI by L square. This condition that you are obtaining, this is equivalent to the condition that which we had obtained earlier for this one. Okay, this P is equal to 4K by L for this simple problem that we had considered earlier. This, whatever you understood in connection with this one, is the same thing that you have to understand in connection with this one. Okay, now there's one difference with that is that there you had just P is equal to 4K by L, only one value, but here you are obtaining multiple values because this n can take different values. We are neglecting that n equal to 0. So n equal to 1, 2, 3, 4. These are going to give us different values of this P. So the smallest, so all of these values are referred to as critical values. And each of these critical values will give us a condition of neutral equilibrium. And among all these values, the first critical value that we obtain corresponding to n equal to 1, that is pi square EI by L square. This is the most famous formula of our entire chapter on buckling. Okay, and it is referred to as, sometimes it is referred to as Euler's load or Euler's critical buckling formula. Okay, and please try to understand this critical load in the same way that we had understood that earlier P is equal to 4K by L. We will discuss this in more detail. I don't want to rush this in the last 2 minutes. So we'll come back to this discussion. But please note that this formula that we have obtained and which was first obtained by Leonhard Euler, one of the greatest mathematicians to ever live. And this was obtained back in 1757. Okay, so I mean long back. So this formula, it pertains, okay, only to this column which has pinned joint at both the ends. Okay, do not forget this. If you have different boundary conditions at the two ends, this formula is going to get changed. Okay, remember that this is only for pinned end. All right, so you please go to your next class. Since we are not going to have any class on Wednesday, we are going to have a class on Thursday. I'll have to record a video for this. Okay, so we have only 2 chapters left now for this this buckling and the energy methods. I will have to record one video for this. I'll do that sometime later. So all the best for your test, and please go to your next class now. Thank you very much.
Sir? Hello,
Yes.
sir.
Yes.
So here, if P is going to be greater than P critical, then will it be unstable in that case, just like in the previous example?
Right. So you are absolutely right. So if P is greater than P critical, it is going to be unstable. However, when P reaches a value which is equal to 4 pi square EI by L square, that can give us a situation, another critical situation also. Okay, but there are certain subtleties involved. I will discuss that. Okay.
Okay, sir.
Yeah.
Thank you, sir.
Thank you. Thank you. Please go to your next
Thank you, sir.
class. Yeah. Thank you.